Okay, so what's parametric mode? Parametric mode is a nice way, it's sort of like polar mode, it's a nice way to deal with non-functions, okay? In fact, you don't even need polar mode, you can use parametric mode to mimic polar mode too, okay? So let's say, for example, let's make up something. Let's say I gave you x as a function of t and y as a function of t. It's almost like vector notation. I'm thinking of xi plus yj, but x and y are functions of time, over time, or whatever t is. T could be a parameter meaning whatever you want, but usually it's over time, right? So instead of y being a function of x is a function of a third parameter t, and y is a function of that parameter t also. So x and y are independent of each other. They can each of them do something different. Then when you graph them together, see what you get. Let's say, I don't know, let's say y equals, let's say x of t is 2t, and y of t is just t. What does that look like? All right, let's find out. Let's go to parametric mode on the calculator. So go to mode, go to change from function mode or polar mode or sequence mode, which we've been using lately, to parametric mode. Then go to y equals, and it's not y equals anymore. It's x is a function of t and y is a function of t. Or x is a function of t and y is a function of t, number 2. Or x is a function of t and y is a function of t, curve number 3. But realize parametric mode is really like vector mode. It's like displacement vectors. Pretend that this describes the displacement of an ant walking across the screen. Okay? What does this displacement look like? All right, let's find out. Let's go, let's put in 2t. Notice when you hit the x key, now it's the t key. Okay, and t. Isn't that what I said? Now let's say I only want this from t equals 0 to 5 seconds or something. So 0 to 5 in a small increment. Let's say 0.1 seconds. Now this is zoom 4. Let's see if that's a good window. So what did I get? I got a what? That's the parametrization of a line. Okay? Now look, trace it. Starts at 0, 0, and you plug in t equals 0, right? Look, plug in t equals 0. Do you get 0, 0? Right, okay. Now, let's see, if I trace it to t equals 1. If I plug in 1, I get 2. If I plug in 1, I get 1. Isn't that what I graphed? 2, 1? Let's trace it for t equals 2. Notice you're tracing on t in this mode. If I plug in 2, I get 4 for x, I get 2 for y. That's what it's graphing, right? But notice what this is. Think of it as a vector from the origin to this point. At t equals 2 seconds, your ant is there. So this is plotting the endpoint of a displacement vector that's changing over time. All right? So at t equals 0 seconds, the displacement vector is 0, 0. At t equals 1 second, the displacement vector is 2, 1. Right? 2i plus 1j. Yeah. So x and y are each independently a function of a third parameter t. Yeah. Right? All right. So when t is 2 seconds, the displacement vector is at 4, 2. It's showing me where the ant is. It's pointing from the origin where it started to where it is at t equals 2 seconds. But notice I went up for t equals 5. How big does this get if you plug in 5? What's this if you plug in 5? If you plug 2 times 5, 10, and just plug in 5, 5, 10. So my window isn't big enough. Let me change my window. How about if I go from 0 to 5 in x and 0 to 10 in y? So I can see the whole trajectory of my ant. There it is. Okay. Wait, what happened there? If I plug in 5, oh, I'm sorry. If I plug in 5, the x's go to 5 and the x's go to 10 and the y's go to 5. I did backwards. Sorry. Let's go. The x's go to 10 and the y's go to 5. I did backwards. Bing. There it is. That's the entire trajectory. If you trace it for t equals 0, 1, 2. Now we can get 3 seconds. So the displacement vector is at 6, 3. We can do it at 4 seconds. The displacement, or anything in between, right? I'm just doing round numbers. The displacement vector is at 8, 4. And after 5 seconds, the displacement vector is pointing to 10, 5. And that's where my ant is. After 5 seconds, he's walking in a straight path, right? Okay, good. Now, what if I change it up a little bit? What if I make this something different? How about cosine of t and sine of t? And let's go back to, I don't know, zoom 4. What do you got now? Well, I didn't get the whole, what am I thinking I'm getting? What shape is that? If it kept on going. It's a circle, right? Why is that not surprising? Why is it not surprising that this is the parametrization of a circle? Because remember when we converted from polar mode to Cartesian mode, x equals what? R, remember this stuff? X equals R cosine theta, and y equals R sine theta. Look, x equals what cosine theta? Y equals what sine theta? What's in front of x? What's in front of the cosine and the sine? What number? 1, so the radius is 1. This is the same thing as graphing polar mode where r equals 1. So I don't need polar mode. If they ever gave you r as a function of theta, like r equals 1, I can graph it here by putting a 1 times the cosine and a 1 times the sine. Look, remember the 3-petaled rows? Remember that? And the cardioids, the limicines, all that weird shapes? Wasn't it 3-petaled rows y equals 3 sine theta? Say? I think that had vertical symmetry. Had 3 petals, right? So if x equals r cosine theta, let's say t is theta, and y equals r sine theta, and r is sine 3 theta, what should I type for x? If r is sine 3 theta in polar mode, how do I write that in parametric mode? Where x equals r cosine theta. So what do I write in front of the cosine? The sine of 3 theta. What do I write in front of the sine? The sine of 3 theta. So I don't need polar mode. Realize that polar mode doesn't really exist. Polar mode, when you plug in sine of 3 theta, whatever, it just does this. It goes to parametric mode. So look, what if I type that in? Let's put in second insert, because I think I'm in override mode, of sine of 3 theta, but I'm using t instead of theta, big deal. And then the same thing down here, second insert, second deleted insert, and sine of 3 theta. I think sine of 3 theta was the 3-petaled rows with the vertical symmetry. So you had 2 petals in the first and second quadrant, and 1 petal coming down on the y-axis. Let's see if that's what we get. Isn't that your 3-petaled rows? There you go. So parametric mode and polar mode are intimately intertwined, right? If you think of parametric mode as x equals r cosine theta and y equals r sine theta, whatever your r is in polar mode, you can just plug it right in. What if, so now let's go back to make it silly, what if r is just 3? What would you expect to see? In parametric mode, if you graph r equals 3, what do you get? Theta can be anything, r is always 3. What is that? R is 3, theta is pi over 4. R is 3, theta is pi over 2. It's a circle of radius 3, right? So let's see, graph that. There it is, a circle of radius 3. Why don't I get the whole circle? Because my t max is only 5. But if you're thinking of t as theta, and you want the whole circle, you got to go from 0 to what? Not 0 to 5. 0 to what would give you the whole circle? 6.2, whatever. It's in radian mode. I'm in radian mode, right? Radian mode. So I got to go from 0 to 2 pi. So 6.28 something, let's say. Oh, what the heck? Just put in 2 pi. And now you should get the whole circle. So you can control the graph based on your t window. You're tracing on t. All right? All right, so that's parametrized motion, or a trajectory defined parametrically. Alrighty. Let's see. All right, let me ask you this. What if I change it up a little bit? What if I put in 20 here, second insert of 20? And what if I put in second insert of 30 here? Whoops, I got too many 3s here. What would you expect to see now? The radius is in the constant then. Along the x-axis it goes 20, and along the y-axis it goes 30. What is that shape? That's an ellipse. Now, if you graph it, why don't you see nothing? Because I made it way huge, right? So I'm saying it's going a radius of 20 horizontally and a radius of 30 vertically. It's a radius that's sort of changing as we sweep the arc of the circle. So it's not a circle, it's a stretched out circle, it's an ellipse. So let's make it big enough. Let's make the window go from, for x, negative 20 to 20. I think that's big enough. Say in 10. And negative 30 to 30 for the y's, say in a scale of 10. So you get the full graph, and do you get an ellipse? There it is. Now that's not a square window, because look, 20 units horizontally is bigger than 30 units vertically. That's ridiculous. It's supposed to be stretched this way, not this way. So when I arbitrarily put in my x min and x max was negative 20 to 20, and y min to y max was negative 30 to 30, I didn't come up with a square window. But I could make it square. Zoom 5. Now is it in fact an ellipse that's stretched vertically? That's what you want to see. So look, this is an ellipse. Now instead of a radius, we don't call it a radius, we call it the semi-minor axis. This is the minor axis, is how big. Let me ask you this. Do you know anything about ellipses? Have you done anything with ellipses? Okay. This is called, this shorter diameter, bigger diameter, right? We call the shorter diameter the minor axis. How long is it? This is 20, so how long is the minor axis? 40. This is 30. How long is the major axis? 60. The semi-minor axis is like a radius, is 20. The semi-major axis is like a radius, is 30. Okay. Just getting some words out there that you're going to be using in this chapter. All right, let me muddy the water a little bit. What if I add to this some weird stuff, like, whoops, where did my calculator go? Okay, let me add to this. Plus something weird, hang on. 4 times the cosine of 4 rad 5, close the rad, t. Close the cosine. And do something similar down here, but make it plus 4 sine of 4 rad 8, t, close the sine, and graph that. What did I just get? This is what's known as a retrograde orbit. Instead of an elliptical orbit. Huh? Yeah, what is that? I don't know. It's sort of like, okay, this is what it is. Pretend you have some planet whose orbit was that thing that goes 30 this way and 20 this way, right? But around the planet is like a moon. And as the moon orbits the planet, it's following the planet around the ellipse. And that's what the moon's orbit looks like. That's called a retrograde orbit. It's not just an ellipse, but it's an ellipse with another ellipse in it, right? Now, it's a little bit choppy. Maybe if I made my t-step a little smaller, 0.05, it might look better. But now that's going to be real slow, so hang on. Time for ludicrous speed. Okay. Turn it off because it goes to sleep real fast. So that's a typical orbit for like a moon around a planet, something like that. All right. So the planet was this. The planet just did this: 20 cosine t and 30 sine t. So I'm going to graph the planet orbit on top. There's the planet's orbit. Again, let's do ludicrous speed because I'm impatient for some reason. Okay. I'm too impatient. Wake up. Okay, there it is. Now, it's not obvious. We could make the planet orbit, I don't know, thick. Let's make the planet orbit thick. So here's the, slow, go. All right, so the thick part is the planet orbit, and the thin part is the moon orbit around the planet. And I guess you could, now are planet orbits elliptical? Planets around the sun, like the Earth, the Moon, the Earth, Mars, Venus, are they elliptical? Yeah, that Copernicus figured that out. No, sorry, Kepler figured that out. Ever hear of Kepler's laws? Kepler's three laws? No? Okay. But it's not too elliptical. The original idea was that it was circular orbits everywhere. It's just slightly elongated, a little bit. All right? So let's make it look more circular, just for fun. What would make this look circular? A circular orbit and a retrograde orbit around it. Make the 20... Do what with the 20 and the 30? Make them the same, right, okay. So how about make them both 20? I don't know. Make them both 20. So now it is a circular orbit as the base. Let's see what that looks like. And I'm impatient. So it probably looks a little bit more like that because the solid orbit, the thick orbit, the planetary orbit is almost circular. It really looks, if you were able to like look down on the solar system from afar and look at the orbits. They are elliptical, they're a little bit stretched out, but not too much, so it looks more like that. That could be, say, a simulation of the Earth with our moon, let's say. Okay? And notice, is that a function? Is that anywhere nearly remotely a function? No. This is a perfect place to be playing around with non-functions, parametric mode. Okay? Alrighty. What if I graphed this? What am I graphing really? Is this a polar example? Is this x equals r cosine theta and y equals r cosine theta? The r's are the same? So what's r? No. What's r? It's t, but remember in this case we're thinking of t as theta. So what if, we just said a minute ago, if r equals a constant, if r equals 3, and you just change the angle, you get a what? Say if r equals 3, r is 3, r is 3, r is 3, you're just changing the angle, what do you get? A circle. Let's go backwards. We're letting r equal 3, theta could be anything. Now, let r equal theta. What the heck does that mean? What does r equal theta mean? That's what I'm graphing. Well, let's see. Graph it. Let's see if this is a good window. I don't know if this is a good window. Oh, ludicrous speed. Ah! What did you get? Actually, you can get Fibonacci numbers from the points that I just graphed. Yeah, you can. But let's not go there because that could take a whole hour. I don't got it. That's interesting side story. But let's not go there. It's like a spiral. Why? Because as theta gets bigger, as you're plotting for bigger and bigger thetas, you're plotting r equals theta, r is getting bigger. So if theta is pi over 2, r is pi over 2. If theta is pi, r is pi. Right? If theta is 0, r is 0. If theta is pi over 4, r is pi over 4. If theta is pi over 2, r is pi over 2. If theta is 3 pi over 4, r is 3 pi over 4. If theta is pi, r is pi. It's getting bigger and bigger and bigger. What if I make my theta max not 2 pi, but I don't know, how about 4 pi? Ugh, ludicrous speed. You know what, I don't really need ludicrous speed here because I don't need such a small theta step for this, I don't think. Yeah, that's a problem. Okay, turn off ludicrous speed. Turn this back on. I don't think I need a big theta step for this. I mean a small theta step for this. How about just point 1 graph? How's that? That's not that much faster, is it? All right, let's see. Wait, hang on. What if I can I just take it? 1 might be too... You see it's not smooth? So if I make my theta step small, I'm going to get a smooth curve. I made theta step big so it goes fast. But you were saying what?
It's the cosine of theta, so what is it?
Well, because what we're graphing isn't cosine of theta. What we're graphing is x is r cosine theta and y is r sine theta. So r in polar mode is theta. That's what we're graphing. So I could even make a theta step even bigger than that. Let's see, theta step, what did I have? 4 pi? How about 8 pi? But why is it so choppy? Because I'm only graphing for thetas 1, 2, 3, 4, 5. So it's skipping a lot of theta, so you're not getting the curvature. Because remember, this thing, what it does is it plots points and then connects the dots. So if the points are close together, you get the illusion of a smooth curve when it's not. It's really a bunch of line segments. So if you want to make this look better, look more correct, maybe 0.1. But now I'm going to need ludicrous speed, I think. Ludicrous speed. There you go. All right, so you get the idea. Ludicrous speed off. All right, so that's called the spiral of Archimedes, by the way. Anyway, that's a famous graph. All right, so that's 14.1. What's parametric mode? Okay, 14.2. What is this? All right, so we're just going to be graphing more stuff in parametric mode. That's all we're doing. Okay. So tell me, what is? Did I turn off parametric? I did. Okay. What if I graph this? You tell me what this is going to be. I'm going to graph, 5 plus 2 cosine t. And I'm going to graph 3 plus 2 sine t. What do you think that's going to be? Good. There's a shift here. Forget the 5 and the 3 for a minute. Isn't this r? Isn't this x equals 2 cosine theta and y equals 2 sine theta? Isn't r 2? So if r is 2, you get a circle of radius 2. But I'm shifting it 5 units in the x and 3 units in the y. So it's a horizontal shift and a vertical shift. So I moved it 3. I'm adding 3 to every x value. So I'm making every x value 3 bigger. 3 to the right. I'm adding 5 to every y value. I get it backwards, sorry. I'm adding 5 to every x value, 5 to the right. I'm adding 3 to every y value, 3 up. So I've changed the center of the circle. It's at 5, 3. It's a circle of radius 2, but centered at 5, 3. All right. So let's see if that's true. I don't know if this is a good graph window for this. Ugh. Yeah, why is it taking forever? Window. Yeah. How about we do zoom 4? Now 5, 3 is a little bit off that screen, isn't it? Okay. See, there it is. Do you see it? Let me change my window to include 5, 3. I don't think I need to go to 0 to 8 pi. How about 2 pi? 0.1, fine. How about 0 to 10 to see x equals 5? And 0 to 6 to see x equals 3. Y equals 3. How about that? There you go. Is that a circle of radius 2 centered at 5, 3? It is, yeah. Well, in this case, no, because the way we wrote it, we're physically taking each x value that we had, the 2 cosine theta, and adding 5 to it. So we're actually making the x values 5 bigger, positive 5. So it is a horizontal shift to the right and then a vertical shift up, right? All right, now, do you know how to write the equation of that circle in terms of x and y? The equation of this circle? X squared plus y squared equals r squared. Not enough. Close. All right, let's see. It's x minus h squared plus y minus k squared equals r squared. Where hk is what? Not the vertex. The center. All right? So, we figured out that the center is at h is, well, it's 5, right? And k is 3. There you go. And the radius is? It was 2, so when you square it, r squared is 4. So that's another way of writing. So look, if we solve for y, what if we solve for y? What if we got y alone? And we graphed it in function mode? You would get the circle. Let's see if that's true. You would get the same circle. Let's see. All right, how do you solve for y? You tell me. How do you get y alone? So I can do this in function mode. Now be careful, is a circle a function? So it's going to be tricky to graph in function mode, but we'll get there. All right, how do you get y alone? Get rid of the x minus 5 squared, subtract it from both sides. Okay, so you get y minus 3 squared equals 4 minus x minus 5 squared. All right, now what? Square root both sides. But remember, what's the square root of 4? 2, or you get two answers, right? So you get y minus 3 equals plus or minus radical 4 minus quantity x minus 5 squared. And one more step to get y alone. Add the 3. So in function mode, this circle can be graphed as 3 plus stuff I'm not getting the 5, and 3 minus stuff. So when you do the y's 3 plus stuff, you get the top half of the circle. The top half of a circle, a semicircle, is a function, right? It's the bottom half that's messing you up, or vice versa. So when you graph 3 plus stuff, you get the functional part of the top half, and 3 minus stuff, you're going to get the functional part of the bottom half. Let's see if we can do that. Go into your calculator. Leave the window, same window, right, as far as x's and y's. Change your mode back to function mode, and graph that. All right, so clear this stuff, and graph that. So it was 3 plus radical. It was 3 plus, right? And 3 minus, yeah. 3 plus radical, 4 minus quantity, x minus 5, all squared. And then I close the radical, and let's see what that looks like, just that. In the same window, whoops, what did I do? I did something weird. What did I do? 3 plus radical. Did I open too many parentheses or something? Open, open, close, close, close. Too many closes. Ta-ding. Oh, I didn't do squared. Okay. I did do squared. What are we talking about? Open, open. I did too many closes. There it is. Okay. So is this a semicircle? Is this part of the same circle we graphed before in parametric mode? It is. It's the same circle. It's just the top half, the semicircle, centered at 5, 3 of radius 2. It's the same piece. Same circle, but it's only a piece of it. How do I get the second piece? What would you write here? Same thing. All right. Do you really want to type all of that? Is there a way to avoid typing all of that? Second, not entry. Recall y1. You forgot recall? Second store is recall. You know store, right? Second store is recall. Vars, y vars, function 1, enter. I don't have to type nothing, except I got to change this to minus, graph. So that's how you graph a circle in function mode. What happened? Why didn't it connect? Because that's where it's not a function. Right? If you connect there, right? If it's hard for it to connect these dots because it can't graph that dot. You can't graph the dot where they're together because of the way the pixelation on the screen. There's not enough pixels to see the edge. If you had a different window, maybe. I don't know. We could play with the window, maybe get it. It should connect. Pretend that it connects. If you play with the window, you can get it to connect. It's missing pixels. It doesn't have enough pixels to get that point to connect. Yeah. That's why I don't like to do this in function mode. I like to do this in parametric mode, right? Okay. All right, so look. This is what a circle, whoops. Where am I? I didn't write it down here. Okay. This is what a circle looks like in parametric mode, right? X of t is h plus r cosine t, and y of t is k plus r sine t. But you know that that translates to x minus h squared plus y minus k squared equals r squared. Okay. Now what I want to do is something completely different. Instead of solving for y and graphing in function mode, we did that, right? What if I just FOIL this out and see what I get? What does this look like? If I FOIL this out and FOIL this out, combine like terms, see what I get, see what it looks like. Let's do that. So x minus 5 squared, y minus 3 squared, and 4, right? So x minus 5 squared plus y minus 3 squared equals 4. So how do you square that out? X minus 5 squared, how do you do that? X minus 5 times x minus 5 is 4. Okay. X minus 5 times x minus 5 is, well, you tell me. First times first, x squared. Outer times outer, negative 5x. Inner times inner, negative 5x. Last times last, 25. So you end up with x squared minus 10x plus 25. Aren't you going to get something similar for the y minus 3 squared? If you do y minus 3 times y minus 3, guess what you get? Y squared minus 6y plus 9. Okay, let's write all that out. So I got x squared minus 10x plus 25 plus y squared minus 6y plus 9 equals 4. All right, so let's see here. Let me regroup this a little bit. All right, can I set this equal to 0 and write this in standard form? Now, what does it mean, standard form? In highest degree first, right? X squared's first, x squared's and y squared's first, x's and y's second. By the way, standard form also includes, if you have two terms with the same degree, write them alphabetically. So x squareds come before y squareds, x's become before y's. So how do I set it equal to 0? What do you do with the 4? Subtract it. And notice they're like terms. There's a 25 plus 9 is what? 34 minus the 4 is 30. So I'm going to write it this way. X squared plus y squared minus 10x minus 6y plus 30 equals 0. And that's what's known as the standard form or general form for a conic. A circle is a conic. What's a conic section? You have any idea what that means? A slice of a cone. Think of a huge ice cream cone, right? You go to Baskin Robbins, right? And you go on, what is it, on Wednesdays they give you free sundaes, on Tuesdays they give you dollar cones, right? Now, pretend the dollar cone is like this huge, enormous cone, right? Huge. Now it's empty. Okay, it's this big, huge waffle cone, right? Okay, can you see it? The pointy down here, circular, or put it upside down. Circular base on the bottom comes up to a point, right? Like that? Okay. Now, pretend it's filled with ice cream, but it's flat on the bottom. It's not a normal ice cream cone. Normal ice cream cone, there's extras. It's flat on the bottom. Now, take a slice. You got a chainsaw or something, okay? You ever see those people with the chainsaws and they do the ice sculptures? Pretend that's what you're doing with your ice cream cone, okay? So slice it parallel to the ground. Take off the top. Look at it. What do you see? A circular cross section, right, of ice cream. You see ice cream, but a circular cross section of ice cream. All right? Put it back together, glue it up, whatever. Okay, now slice it a little bit less, a little bit off of parallel to the ground. Take off the top. What do you think you see? You don't see a circle anymore. You see an ellipse. These are conic sections, slices of a cone, right? A circle, an ellipse. What if you slice it so it hits the ground? You slice it, right? It's not parallel to the ground, not a little bit off parallel to the ground, but hitting the ground. Now you take off that piece of the cone. What do you get? It's a parabola. Now this is a really weird ice cream cone. Are you ready? It's flat on the bottom, circular bottom, say a radius of 5 inches or something. Make it big, 5 feet. Okay? Comes to a point, right? Now, say it's 2 for Tuesdays. You got another one. You got 2 of them. And you put that one going this way from the point up. Right? So you got a cone going like this and a cone going like this. They touch at the tips. Okay? What if you slice through the top one and through the bottom one? And you take off the slices. And now you look at the cross section. You got a piece here and you got a piece here. When you have 2 branches, we've seen that. That's not a parabola, that's a hyperbola. So hyperbolic conic section, or cross section of a cone, parabolic cross-sections, elliptical cross-sections, circular cross-sections. By the way, circles and cones are very similar. They can all be written like this. Ax squared plus, well, there's a missing term. You sometimes have an extra term. Ready? Sometimes you have this. Ax squared, a certain number of x squareds, plus bxy. Do you see any xy's up there? You see any xy's up here? No, so b is 0. Okay, you can have it. Plus cx squared, y squared, plus dx plus ey plus f equals 0. Where a, b, c, d, e, and f are just real constants. Okay? Depending on what the values of a, b, c, d, e, and f are, you're going to get a circle, an ellipse, a parabola, or a hyperbola, depending on those values. Okay? Now, we graphed this thing. This was a circle, right? This was a circle, right? The one we just did? Now, remember the quadratic formula? Remember the quadratic formula? Negative b plus 1 is the square root of what? B squared minus 4ac? That same discriminant tells you what you get. If you do b squared minus 4ac, and you get a negative, that's an ellipse, a negative number. If you do b squared minus 4ac and you get a positive number, you get a hyperbola. By the way, an ellipse can be a circle. Just think of it as a circle where the semi-major axis, semi-minor axis, it's an ellipse where the axes are the same. Okay? So ellipse covers circle. So if you do b squared minus 4 times a times c, and it's negative, that's an ellipse. B squared minus 4ac, and it's positive, that's a hyperbola. If b squared minus 4ac is 0, you might get a parabola, or you could get a degenerate. What's a degenerate conic? Who's the black sheep of the family? What's a degenerate conic? Think of it, for example. What's a circle of radius 0? Think of a circle like this circle, centered at 5, 3, but the radius isn't 2, the radius is 0. It's a point. Just a point. That's a degenerate conic. You could get that. When b squared minus 4ac equals 0, you can get a parabola, but you might get a degenerate. Think of this, too. See the cone? The two cones? What if I slice... Now, how would I have to slice these cones so I hit one point? I have the big cone here and a big cone here. Where would I have to slice it to get just one point in my cross-section? Right down through the tips, right? Okay. Is there a way I could slice it so I get a line? Is there a way I could slice through the cones so I get a line? What if you don't really slice? What if you just sort of tap the edge, the outside edge of this cone through the tip, and the outside edge of this cone? So think of your knife or your chainsaw, whatever it is, as a plane that's tangential to the side of the cone, and the tangent points form a line. That's also a degenerate. You can get a line. So if b squared minus 4ac is 0, you might also get a line. All right, so what do you get? What's a in this example? What's a? 1. What's b?
0.
There isn't a b. What's c? It's 1. So what's b squared? Since b was 0, you just told me b was 0. What's b squared? 0, right? Minus 4 times a times c. What's 4 times 1 times 1? 4. So b squared minus 4ac is 0 minus 4 is negative 4. So what shape is it? Positive is hyperbola, 0 is parabola or degenerate, negative is an ellipse, which includes a circle. It's elliptical. Circles are considered ellipses, right? Okay, why? Why are circles considered ellipses? Well, think of it this way. What if I said x, what was it, x minus 5 squared plus y minus 3 squared equals 4, right? Is that what I had? What if I divide everybody by 4? X minus 5 squared over 4 plus y minus 3 squared over 4 equals 1. That's still a circle, right? What is that? That's elliptical form. This is circular form, this is elliptical form. Why is this called elliptical form? Because what if the 4s are not the same? What if the 4 here and the 4 here don't match up? Then it's not a circle. What if it's a 4 here and a 9 here? What do you suppose happens? The horizontal radius is 2, the vertical radius is 3, that's an ellipse. That's what an ellipse looks like, where the radius is changing. Okay? So this, I would call, usually the semi-minor axis is called A, so this would be A squared. And the semi-major axis is called B, that would be B squared. Right? So, you could write a circle this way, but you could write an ellipse this way. X minus H squared over A squared plus Y minus K squared over B squared equals 1. If A and B are equal, that's a circle. If A and B are not equal, that's an ellipse. But it's still centered at HK. It's still like a circle centered at HK, but it's not a circle anymore if A and B are different. If A and B are equal, it's a circle, right? Okay. All right, good. All right, now, let's go really nuts. Are you ready? What if I just gave you that? I just gave you that. Could you graph it? Now, pretend you don't know it's a circle of radius 2, center to 5, 3. We know that already. Top secret, don't tell anyone. Is there a way, starting with this, is there a way to get there? Get to the point where you know it's a circle of radius 2, centered at 5, 3. Can you change the general form conic to standard form conic? So it looks like a circle, or it looks like an ellipse, or it looks like a hyperbola. You got to complete the square. Did you just say that? You just said that. He just said that. Wow, that usually takes a lot of coaxing. Good. Okay. Let's do that. No, don't do the update. Oh, jeez. All right. So 20/20 hindsight. I know the answer. Let's see if I can get it. I want to end up with x minus 5 squared plus y minus 3 squared equals 4. I want to end up with that because I know that that's what this is. But let's pretend I don't know that. How do I get that? Okay. You can use completing the square to figure this out. All right, so what is it now? It's x squared plus y squared minus 10x? Okay. X squared plus y squared minus 10x, what the heck was it? Minus 6y plus 30? Okay. Minus 6y plus 30 equals 0. Now, using this technique of completing the square, I can get this into circular form, standard circular form, standard elliptical form, or standard hyperbolic form if as needed. Question on the test tomorrow is like this. What? I didn't say nothing. I didn't hear it. Did you hear it? I didn't hear it. I didn't hear it myself. There's a question like this on the test tomorrow. All right? What you need to know about conic sections tomorrow is basically what I'm doing right now. Are you ready? I didn't say that because I'm not supposed to tell you anything about the test. All right. So how do you complete the square? Well, I want to end up with x minus h squared plus y minus k squared. So first thing you're going to do is get all the x stuff together, all the y stuff together, and get rid of everybody else. Do you see what I'm saying? I don't have all this x stuff together. What do I want to do? I want to write x squared minus 10x. Okay. X squared minus 10x. Leave a little space. Plus y squared minus 6y. Leave a little space. Equals, how do I get rid of that 30? It's in my way. Subtract it, negative 30. Okay? Have you ever seen this stuff using completing the square to get standard form conic sections? Okay. Maybe not, that's why I'm doing it. Okay, so how do I complete the square? I want to end up with a perfect square. I want to end up with something like x minus 5 all squared. So I want a quadratic that factors with the same factors twice, right? Real, rational, equal roots, same factors twice, remember that stuff? How do I get this to be a perfect square? Something minus, x minus something squared. You remember we did a little completing the square stuff, right? When do you get a quadratic that factors such that both factors are equal. This is when. When the number you have with your x is half of that negative 10. Now, square the negative 5. What do you get? 25. Add that over here. Right? Now, this is what I'm saying. If I factored x squared minus 10x plus 25, I would get this. Because negative 5 times negative 5 is positive 25, and negative 5 plus negative 5 is negative 10. Isn't that how you factor? Okay, but notice I messed up the problem. I added 25 to do that. I'm replacing x squared minus 10x with something it's not equal to. I'm replacing x squared minus 10x with something that equals x squared minus 10x plus 25. So when I replace it with this, I'm effectively adding 25 to this side of the equation, so I better add 25 to both sides of the equation. Did we do some of this somewhere? Yeah, we did. Yeah.
When you divide by 2,
Where did I divide by 2?
well, the 10, when you divide the 10 by 2.
Oh, when I divided 10 by 2, yeah.
If it was positive 10,
Then you would end up with a positive 5, yeah. You always, when you square this thing, when you square the negative 5, you're always going to get a positive here. But if this is negative, this is negative, this is positive, this is positive. Right? But when you square it, it's still going to be positive. So we add 25 here, but add 25 over there. Okay, let's do that. I'll put that somewhere. How about up here? Plus 25. All right, so what are you going to do with the y's? Same idea. What are you going to do with the y's? Plus what squared? Plus what squared? Y minus 3. You take the negative 6. It's a negative 6. Yeah. It's a negative 6, right? You divide the negative 6 by 2 and you get negative 3. So y minus 3. But when you square that out, what do you get over here? Plus 9. And again, the plus 9 wasn't part of the problem. So when I replace this with this, I'm effectively adding 9 to the left-hand side of the equation. I better add 9 to both sides of the equation. So what do you get over here? Don't you get 4? Right? 25 minus 30 is negative 5 plus 9 is 4. And isn't that what we said was going to be? A circle of radius 2 centered at 5, 3. We're pretending not to know. Right. So this is what you're going to see. One of the questions on the test tomorrow. I'm going to give you this. I'm going to ask you to do this and graph it. Can you graph it? Because of the plus 9 and the plus 25. Right? All right. Is this a terrible thing? I hope it's not. Okay. All right. What if you had an ellipse? Let me show you an ellipse. Ready? This is an ellipse. Parametrically. X of t is 7 plus 2 cosine t, and y of t is 4 plus 5 sine t. How is this different? Why is this not a circle? It looks a lot like the circle, doesn't it? What's different about it? The circle was what? H plus r cosine, k plus r sine. These are supposed to be the same. So guess what? That's the horizontal radius, the semi-minor axis. That's the vertical radius, the semi-major axis. By the way, the major minor means big or small. So it's not always, the horizontal is not always the minor. If the horizontal is big, it's the major. Yeah. And that's just arbitrary. Which one is the major, right? Which one's long? Right? So the minor axis, semi-minor axis is 2 along the x-axis or horizontally, and the semi-major axis is 5 vertically. All right. So what does that look like? Well, it's still centered where, though? Where is it centered? 7, 4, but it's stretched out 2 and it's stretched out 5. All right, let's see what that looks like. Let's go back to parametric mode and see if we're right about this. What's parametric mode? Mode. Parametric. Okay, y equals, okay, so it's not this. It's 7, 2 cosine, and it's 4, 5 sine, right? And that may not be a big enough window for this. Well, sort of. All right, so if it's centered at 7,4, 7,4, and it has a horizontal radius of 2 and a vertical radius of 5, does it make sense that it goes down below the x-axis like that? It does, right? So to see the whole thing, I would make it a little bit bigger, I guess. Let's say window. My y min would have to be at least down to -1, and at least up to, let's see, 4 and 7 up to 11, let's say. So window, change your y min to at least -1, at least as low as -1, and at least as high as, what, 11, I think. Right, because if it's at 7,4 and then up 5, it's 9, 9, 9. And there's the whole ellipse. It may not be a square window, but you still see that it's stretched vertically. That's pretty good. Okay? And again, it doesn't connect because of pixelation. Don't worry about that. Alrighty. So guess how you write that in terms of x's and y's? How would you write that in terms of x's and y's? X minus, what do you think? Sort of like the circle. X minus 7 squared plus y minus 4 squared equals 1. Now I'm going to write this elliptical over what? Remember in the elliptical form we took the radius and we divided everybody by it, so we had a 1. So it's a squared b squared. What's a squared? Not 49. 4. And what's b squared? 25. There you go. That's how you write it in terms of x's and y's. Now, what if we did like last time? What if we solve for y and graph this in function mode? What will you see? If I solve this for y and graph this in function mode, what will you see? The same thing, except it's got the top branch, right? The top semi-ellipse and the bottom semi-ellipse. What if we FOIL this all out and rewrite it and combine like terms and get it in general form? What will you see? Ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, right? In that format, can you complete the square and get back to this? Right? That's what I need you to be able to do. I'm going to give you a general form, and I want you to get to this form, and I want you to graph it. Okay? Question?
Is it always equal to 1?
Yeah, when it's an elliptical form, it's always equal to 1.
How did you get the 4 and the 25 again?
Because it's the 2 squared. It's like the radius squared here and the other radius squared here. Because the radii are changing. All right, so let's FOIL this out. Okay, let's FOIL this out, see what it looks in general form, and let's see if we can undo it. Okay? Let's FOIL this out. All right, so it's going to be x squared minus 14x plus stuff. Well, if you FOIL that out, don't you get 49? Yeah, 49. But that's over 4 plus what? Y squared minus, not 16, 8y plus 16. Is that what you're thinking? Plus, yeah, okay. All over 25 equals 1. Now, is that general form? Is that ax squared plus bxy plus cx squared, cy squared? Is that general form? No, I got to get rid of the 4 and the 25. How do I get rid of that? I shouldn't have any fractions. Multiply through by the common denominator is 100. All right. So multiply everything by 100. I get 25x squared minus, God, 14 times 25 is a quarter of 1400 is 350. Is it 350? Huh? Square root of 25? Oh, I wrote it wrong. I'm sorry. Wait. 25x squared minus what? What's 25 times 14?
What we doing like that's 3?
I'm just multiplying everything by 100. So the 4 cancels and the 25 cancels.
Oh, okay.
Okay? Right? Do you see? Right? So isn't it what? 350. It is 350. Okay.
Wait to get the common denominator.
The common denominator is 100.
Yeah.
Now, if I multiply everybody by the common denominator, the denominators will cancel. That's my idea. I don't want any denominators, right? The general form has no denominators. The elliptical form does. Okay. So minus 350x plus, God, 4,900 times 25. 49 times 25 is 4,900 divided by 4 is what? 2250? 1225? Oh, half of that, right? 1225. 1225. Wow, okay. Plus, I'm going to write it down here. 4y squared minus 32y plus 48. What am I doing? I'm multiplying by 4 because the 25 cancels into 100 4 times. Equals multiplying both sides by 100. All right, now is that general form? Is that complete? No, because it's got to be 25x squared plus so many xy's, there's no xy's, plus so many y squareds, plus so many x's, plus so many y's, plus so many constants. It's almost there, but we can get it. All right, I'm going to write this. Now, also notice there's a constant 1225 here, a constant 48 here, but I want 0 here. What do you do with 100? Subtract, right? So it's 2225 plus 48 is, 1225 plus 48 is 1273. Minus 100 is 1173. Okay? Let me write this down somewhere. Let me write this down. All right, so it's 25x squared plus 4y squared minus 350x minus 3y plus 1173. Okay. All right, so this is what we ended up with. 25, whoops, 25 x squared plus 4y squared minus 350x minus, was it 3y? Yeah, I just realized that. What's that again?
It should be 48, it should be 64, and then it should be minus 32y, right?
It is 64, right, you're right. Okay, just when I thought I knew what I was doing. All right, this is 64. And what else?
Your y is negative 3, it should be negative 32.
Negative, I said 32, I wrote it too fast. Right, 32. Yeah, okay. All right, oh, I can copy it from here, okay. So it's 25x squared plus 4y squared minus 350x minus 32y, right? 32y. And then if you add these up, okay, this is different. So it's 1289, right? Minus 100 is 1189. All right, so say I started there. Say I gave you that. How would you complete the square now? Would you be able to convert this back into circular or elliptical or hyperbolic form? We haven't talked about hyperbolic, we will in one second. And graph that? How? First, what's different here? First, you got to get rid of the. Right, what was the first step last time? Get the x's together, get the y's together, get rid of the numbers, right? So pretend you have the x's together. What's different is I got that 25 in front. I don't know how to complete the square unless there's a 1 in front, right? Remember the process we figured out for completing the square always had a 1 in front? How would you get a 1 in front? I have 25x squared minus 350x. How do you get the 1 in front? First thing you do is factor it out. And then do the same thing. Right? So what about the 4y squared and the minus 32y? First thing you're going to do is you're going to factor out the 4. All right, so let's pretend we don't know the answer, right? 20/20 hindsight, we know the answer, but we don't. Can I get this in the form that I can graph it without a I can't graph that with a calculator, right? I could get it into elliptical form, and then I know how to graph it. I know the center, I know the semi-major axis, I know the semi-minor axis, right? Okay, so let's rewrite it. 25 x squared minus 350x plus 4y squared minus 32y equals negative 1189. Okay, let me clean that up a little bit. Pretend that's a y, okay? All right, so first step now, after we get the x's together, the y's together, the numbers out of the way, now factor out the 25, factor out the 4. All right, so I'm going to get 25 times what? X squared minus, now remember, we know where the 350 came from. Wasn't it 14? Yeah, it was 14. So if you didn't know it, you could divide it out on your calculator or whatever. And then factor out the 4. My y's are not working out here. My squares and my y's are not working out. My 8's. Nothing's working out. Okay. All right, now do the completing of the square just like before. You take the negative 14, what do you do with it? I factor out the 4. 4 times negative 8 is negative 32, right? So 4 into 4 is 1, 4 into negative 32 is negative 8. So now what do you do with the negative 14?
What form are you trying to put it in?
I'm trying to get it, well, whatever form it works out to. I don't know, pretend I don't know yet. It could be a circle, it could be an ellipse, it could be a hyperbola. Now, circle and ellipse are similar. Ellipse and hyperbola are similar. We'll talk about that in 1 second. So take the negative 14 and chop it in half. So you got 25 times x minus 7 squared. Now what do you do with the negative 7? Add it. So plus what though? Not 7. 49. Okay, so plus 49. So what do I have to do to both sides? I added 49 there, so I have to add 49 to both sides? No, I didn't add 49. What did I add? What if it distributed the 25 back in?
Oh, 49 times.
49 times 25 is what? That's the 1225. So now I got to add 1225 to both sides.
Yes.
Doesn't it sound familiar? We're doing everything backwards, so it should sound familiar. Okay. Plus 4 times what squared?
4.
Y minus 4, right? But then you're going to add 16 inside, but 16 inside really means 16 times 4 is stuff 64. Okay, so I'm adding 64. So what do I actually get? Because it's 4 times 16. The 16 is inside the parentheses. So I'm not adding 16, I'm adding 4 times 16, because the 4 distributes back in. Right? I'm not adding 16, I'm adding 4 16s. I'm not adding 25, sorry, I'm not adding 49, I'm adding 25 49s. Because of the 25 in front, right? So because of the 4 in front, I'm adding 4 16s at 64. All right, so equals what? Add that up, what do you get? Is how much? Wait, wasn't it? I thought it was supposed to be 100. Well, let's pretend it's 100. We might have done something arithmetically weird somewhere, but it should be that 100 that we had before. Okay. So now, is that elliptical?
Yes.
No, because the elliptical form ends in equals 1. The elliptical form ends in equal to 1, right?
Well, yeah.
So how do you get it to equal 1? Divide everybody by 100. So you get x minus 7 squared over 25 over 100 leaves 4, plus y minus 4 squared times 4 over 100 is a 25th, equals 1. So is it still centered at 7, 4? Right? And is the horizontal, the minor axis 2? And the major axis 5? There you go. So you know how to complete the square with when there isn't a 1 in front. I just divided everybody by 100. This stuff adds up to 100. Then I divided everybody by 100. 25 over 100 is 1/4. 4 over 100 is 1/25. Right? Just divide by 100.
How'd you get 14x on the plate?
The 14,
Yeah,
this guy?
on top.
when I factor out at 25. 25 into negative 350 is negative 14. Just factor it out. All righty. All right, so now, do you know how to graph that by hand? What do? You pretend you're graphing a circle centered at 7, 4, but it's not a circle. It has a horizontal radius of 2 and a vertical radius of 5, so let's do that. All right, so what if I graph that? At 7, 4, is the center. Say it's there, right? Then I want to go 2 to the left and 2 to the right. So from 5 to 9 is the minor axis. And then I want to go down 5, so it goes down to negative 1. And up 5, ooh, it's not going to fit. 1, 2, 3, 4, 5. Pretend that's 5. It's not quite to scale, but so up there. And then connect the dots. But of course, I squished it a little bit up here. It's not going to look right, but you get the idea. You could do this on paper. It should look more like this, flipped over on top, right? All right, so there it is. That's easy. That's how you graph an ellipse, okay? So, let me give you another ellipse. Is this okay? Are you okay with this progression? Given this, you get this, and you graph that. Can you do that? This is what you need to know how to do. Given that, can you get that, and can you graph that? Is that okay? That's it. That's all you need to know. All right. Now let me ask you about this ellipse. X plus 2 squared over 4 plus x, that's not x, y minus 3 squared over 9 equals 1. How do you graph that? You start, where's the center? Where do you start? Negative 2, positive 3, right? Because it's x minus h. What does h have to be to get a positive 2? It has to be negative 8, negative 2, right? So the center is at negative 2, positive 3. And the minor axis, horizontal axis, is a radius of 2. Vertically, it's a radius of 3. Okay. So, do you see it? You can graph it in your head. I did it, right? Okay. Now, huh? Square root of the 4, square root of the 3 is the radii, right? Okay, but wait. What if it's this? Guess what that is? That's an ellipse that blew up. Like Bill Nye yesterday said, in space, you don't hear them scream. Right? Did you get that part? He was making fun of the movie Aliens. In space, they can hear you scream. No, they can't. There's no air to carry the sound. So if it goes poof, it goes. You don't hear it, right? So anyway, it's the ellipse we just graphed in our head, right? You see the ellipse with the plus? If it had a plus, it was an ellipse, right? Blow up the ellipse. Pretend to draw the ellipse, but don't. Okay? Look, this is what you're going to do. This is how you do it. Ready? Start at the center, negative 2, 3, right? Negative 2, 3 is where? That's in the third quadrant. So let's make room in the third quadrant. Let's like blow up the third quadrant. Isn't the center negative 2, 3, second quadrant, sorry, second quadrant. Negative 2, 3, second quadrant. So I'm going to blow up the second quadrant. Why is this not giving me geometries? I'm going to blow up the second quadrant. All right. So negative 2, 3 is here. Okay? Now, go to the left, what? What's the semi-minor axis, you said? Go to the left, what? 2. Okay, so I'm going to go over to negative 4. That's a point on the ellipse. The center is not a point on the ellipse. It's just in the center. And then go to the right 2. I guess it hits the y-axis, right? Because this is negative 2. So it goes from 0 to negative 4 for the minor axis. Okay, fine. And then from the center, you're going to go up and down what? So go down 3. At 3, so down 3 is down here. and then up 3, right? 1. Yeah. 1, 2, 3 stays up here, right? 6 stays like that. It's a little squished, sorry. Okay, now do you see the ellipse? If you connect those x's, right, in elliptical format? Don't. This is what you do. Box the ellipse. Let the ellipse live in a box. Okay? And the y-axis and the x-axis, right? Connect. Okay, I'm going to make this a different color. Connect the corners to make the diagonal of that box. Pretend it hit both corners. Pretend it hit at both corners, okay? And the ellipse looks like this. Not the ellipse. The hyperbola looks like this. Where's the mouse? Mouse, where'd you go? There it is. It goes like this. Asymptotically to those lines. These are asymptotes. These are slant asymptotes. The green thing is the hyperbola. So instead of graphing the ellipse, you graph the ellipses exploding out of the box. That's the hyperbola. So if it had a plus sign here, you would just make the ellipse. No box, no red line, nothing. If there's a minus sign in here, draw the diagonals, use them as asymptotes. Now, wait. The hyperbola has horizontal symmetry if it starts x stuff squared minus y stuff. But the hyperbola could very easily have gone up here too. How would I have a branch here and a branch here? If it was reversed. So if it was backwards, if it said y minus 3 squared over 9 minus x plus 2 over 4, x plus 2 squared over 4 equals 1, instead of graphing the green stuff here, I'd graph a green branch up here and a green branch down here. This is part of the hyperbola, goes asymptotically to the red line. This is part of the hyperbola, goes asymptotically to the red line. You see how you graph a hyperbola? You graph like an ellipse, but you don't. Okay? All right, I'm going to leave it at that for YouTube. YouTube, thanks for visiting. Goodbye. This is our last video of the summer. Have a nice summer. Bye.